Hello, everyone. Thank you for attending this Ether public webinar that will revolve around, first of all, an overview of the project, because several of you, I guess, you are not aware of the project, although we are very close to its conclusion. We will present the key achievements and our successful demonstration activities that are related to the three Ether use cases. So we have come a long way. So it's around 3 years and 3 months since the beginning of the project, and we are happy to present you what we have achieved so far. So to start quickly with the agenda, we will go, first of all, as mentioned, through an overview of Ether, and we will also present the key features that enable the sustainability of the proposed 3D architecture through a techno-economic analysis. Then we will go directly to the use cases, starting with use case 1, where we'll present the technical and impact overview, and then a video with a demonstration activity. And we will take also some questions. And the same structure holds also for the other two use cases, use case 2 and use case 3, and we will have some final concluding remarks at the end. And just to mention that the presentation today is undertaken, apart from me, by my colleagues, Agapi Mesodiakaki, Timo Kellerman, Hamad Al-Shar, and Godfrey Kilbaya. So, starting with an overview of the project, in a nutshell, Ether is an acronym that comes from the self-evolving terrestrial, non-terrestrial hybrid networks. It is a call one project, so...
Constantino, sorry, I think you are not sharing the screen.
Sorry. Yeah. Just a moment. Right. Share sound. Yeah. Now, fine. I guess you can see it now, right?
Yeah. Indeed, yeah. Yes.
So, in a nutshell, Ether comes from the self-evolving terrestrial, non-terrestrial hybrid networks. And it is a call one project. So it was granted in this stream B, 0103, titled Communication Infrastructure Technologies and Devices. The goal of Ether is to provide a framework for the terrestrial, non-terrestrial network ecosystem that involves an efficient zero-touch resource management, the provision of solutions for key radio access network challenges, and the identification of the business opportunities for potential stakeholders. It involves 13 partners that comprise 8 industry ones. Among them are 5 SMEs and 5 academic partners. There is a complete chain in the project regarding the involved partners. So we have technological solution providers, such as ourselves, that we are the project coordinators, the Aristotle University of Thessaloniki, the Collins Aerospace that acts as a technical coordinator, I2CAT, Nearby Computing, and the National Center for Scientific Research, Demokritos, and the Lincoln University. We have a mobile network operator, Orange for Poland, 2 satellite networks operators, the big operator Avanti, and the one from Spain, the SME Sateliot. We have an integrator, Ubiware from Portugal, and Collins Aerospace again that acts as the end user. And we have an external advisory board board that consists of the European Space Agency, represented by Maria Guta, and SCS that is represented by Joel Groth. This is the Ether vision. This is the 3D ecosystem that comprises the terrestrial layer, the aerial layer that involves aerial nodes such as high-altitude platforms, drones, and planes, and also the space segment that involves the satellites in different orbits, such as the low Earth orbit, medium Earth orbit, and the geostationary orbit. The idea of Ether came from this excerpt that you see on the right that reads us by adopting a hybrid network, NTNs can offer significant CapEx and OpEx reductions compared to deploying only terrestrial base stations to achieve the same amount of coverage. And according to this excerpt that was provided by a UK consultancy company, to provide a full 5G coverage across the UK would require tens of thousands of additional terrestrial sites, whereas the same coverage could be achieved by only a fleet of around 60 hubs. So the numbers are staggering here, and we understand what the importance is of having this 3D network, this unified ecosystem. So we have innovations that concern low-level technological enablers and high-level ones. In the low-level ones, we have the direct-to-handheld device access. You see in bold the partners that are involved there, us and the National Center for Scientific Research, Democritos. Unified waveform, particularly we studied OTFS as an alternative to FDM, in order to tackle the high mobility, the high velocity, particularly of Earth satellites that induce high Doppler shifts. We have handovers, vertical handover innovations coming from the Aristotle University of Thessaloniki, and also horizontal ones that are being jointly investigated by Sateliot and ITUCAT. We have semantics-aware data analytics coming from Linköping University that concerns the reduction of data that is produced by IoT devices that enables the high reduction of their energy consumption. We have innovations related to mobile computing and caching coming from nearby computing and Linköping University. Flexible payloading, software-defined payloading on board the satellites. That these innovations coming from ITUCAT and University of Luxembourg. And we also have AI-based predictive analytics that are coming from Net AI. And apart from these low-level enablers, we have also high-level enablers that have to do with the management and orchestration of the network. So we have innovations regarding to NFV Mano coming from nearby computing. Also, innovations related to the end-to-end network and service management coming from ITUCAT. And finally, AA enable end-to-end network performance optimization. So we are talking about the joint algorithms that jointly examine the computation, communication, and storage ecosystem coming from Aristotle University of Thessaloniki. And also to finish with the fact that 4 of these enablers drive the sustainability of this network, as it will be also mentioned in the use case description, how these enablers are included. And these are the AI, artificial intelligence enabled end-to-end network performance optimization, the mobile edge computing and caching, the semantics-aware data analytics, and the seamless vertical handover. Now, going quickly to the Ether objectives, we have 5 well-defined objectives. First of all, to provide solutions for the unified and sustainable radio access network for the integrated terrestrial and non-terrestrial network. Secondly, to provide an AI-based framework for the self-evolution network service management and orchestration of the integrated network. So to automatically adjust the management policies and allocated resources based on triggering that corresponds to unknown environments and situations. Thirdly, to architect a viable, highly energy and cost-efficient 3D ecosystem that offers seamless and continuous connectivity. The fourth one is related to experimentation activities to showcase our achievements regarding the innovations. And finally, the identifications of the key benefits that will drive the investments in this integrated non-terrestrial with terrestrial ecosystem. Some few words about the key achievements related to the technical work packages, starting with work package 3 that is titled as Key Technological Enablers for the Seamless and Energy Efficient Ether Network Operation. So some key results here are the channel modeling and link budget analysis in the KI band. So we targeted the 28 GHz band, a terminal antenna design that enables electronic beam steering in order to track the satellite and LEO satellites in order to enable sufficient gain to close the link. We have studied designs of large antennas like 20 by 20 elements and also a smaller one of 4 by 4 that has been prototyped. We studied OTFS, as mentioned before, so unified waveform design, and we also studied some versions that have a reduced complexity. We also studied the LEO satellite flexible payload framework. We provided that, which has been tested on an FPGA platform that is representative of a real payload hardware based on this Xilinx family. Dynamic spectrum allocation solutions for the coexistence of the terrestrial and non-terrestrial spectrum, so effectively mitigating the interference through these solutions, through these algorithms. And semantics aware information handling framework for minimizing the amount of data generated, transmitted, and processed without compromising the conveyed information, and the seamless horizontal and vertical handover solutions. Then we go to work package 4, that is more related to the higher level enablers to the management and orchestration of the network, that is titled as Zero-Touch Data-Driven Network and Service Orchestration in the 3D Architecture. So some key results here are the AI-driven orchestration framework for the proactive zero-touch management of the network and service functions in the 3D Ether architecture. The development of a cloud continuum orchestration framework for the seamless management of the heterogeneous compute resources. Thirdly, we have a development of an SDN-based control plane that is capable of managing multiple domains. Then we go to an optimization algorithms to efficiently allocate SDN controllers across the 3 layers, the terrestrial, aerial, and the space one. Then we will proceed with an energy-efficient joint communication, computation, and storage allocation framework. So we have provision of such algorithms that target the end-to-end Ether network performance optimization, and they achieve up to 6.5 times higher energy efficiency compared to state-of-the-art approaches. And finally, we have developed an AI-enabled framework for forecasting network performance and topology across the 3D Ether ecosystem. The final word from me is about the experimentation activities and the related work package 5, that titles, just a moment, as technology integration and live demonstration of Ether technologies. And the key results are the KPI achievement related to the 3 use cases through the demonstration activities. And the title of these use cases that we will see their analytical description later on. First of all, starting with the use case 1, we have the flexible payload enabled service provisioning to semantics aware and delay tolerant IoT applications. The second use case is related to the direct to handheld device access. And the third use case relates to airspace safety critical operations. As mentioned, we will analytically see later on about the concepts of these use cases and the related demonstration activities. So, having said that, I would like to give the floor to Agapi Mesodiakaki to present the features of the sustainable Earth 3D architecture that are related to a techno-economic provided analysis. So, Agapi.
Thank you very much, Konstantina. So, hello everyone. My name is Agapi Mesodiakaki. I'm a senior researcher with Aristotle University of Thessaloniki, and I will try to dive you into the way that Ether works towards sustainability. We will speak about 2 different things here. The first one is the techno-economic analysis that we have performed, and the other one is the architecture evaluation, and specifically this 3D Ether architecture. So across all the results I will show in the slides to come, we have, of course, a detailed modeling, and you can see that we also have thorough channel modeling, path loss modeling, specific metrics that we focus on. What I would like to stress here is that the path loss modeling we take into account is based on well-referenced documents from ITUR, both for rain, gas, fog, and scintillation attenuation, which is really important in these, including non-terrestrial links. At the same time, we focus on all parts of the network. That means both the access network and also the transport. So speaking about X-haul. And the metrics we focus are mostly also depicted on the slide. So energy efficiency, spectral efficiency, maximum capacity, and cost efficiency. You can see also the formulas we use. They're really well documented. For the energy efficiency, what we've tried to do is to minimize the power consumption subject to a specific data rate demand. So we try to have this quality of service being satisfied and do that with the minimum power consumption being involved. For the cost efficiency, we focus on the TCO. So that means both the CapEx, the capital expenditure, and the operational expenditure, what we call OpEx. And of course, doing that again while satisfying the quality of service of our demands, of the user's demands. Go to the next slide, please. So for the analysis, I will show first that the techno-economic analysis. We focus on both the three layers, so both the terrestrial one, the aerial, and the space one. For the aerial, which I think is the one that is not so much mature, let's say, compared to the others, we consider two different cases. We have the nodes that are, as we call them, low altitude platform systems that are called LAPs, and also the high altitude platform systems. For the second category, so the ones that are called hubs, we have two different categories. The first one is called aerostatic, which actually they're lighter than the air. And the other one is called aerodynamic, that they are heavier than the air. And that's why they have to do some kind of circle movement around the point that they are put in order to, and they also look like airplanes. You can see some aerodynamic features there in the photographs. For the first category, we have two different types of aerostatic nodes. The balloons that I'm sure you're familiar with, and also the airships that they're really promising, and I will come back to this later on, that they look like Zeppelin ones, as you see in the picture. Now, for the low altitude ones, we consider both, all three different categories. So the ones that they have rotary wings, and they are capable of vertical takeoff and landing. Also, the ones with fixed wings that they can carry higher payloads. And again, some hybrid solutions that they combine benefits of both worlds. Go to the next slide, Konstantina. So here we have done a very thorough comparison among different flavors of different nodes in the different layers I spoke about. You can see a lot of things and details about the references we used and so on in our papers. We have some, of course, all of them are also in the website of ITER. What I would like to stress here is that we have so many alternatives, and we have to select the best one among them. Of course, these nodes come with different capabilities, and you can see here some criteria we have identified. For example, the height to which they operate, the flight duration, how autonomous they are, which means in how much time we have to take them down and have some kind of maintenance, the coverage, and also the cell radius. Here, I would like to stress that although the coverage refers to the maximum cell radius, so the further the signal can go, let's say it in really simple terms, most of the times they operate in much smaller ranges, and that's why we also identified both criteria here. The two-way delay, that of course the propagation delay plays a really important role here, and their payload capability. So the kilos that they can, if it's kilos, of course, that they can carry in terms of telecom equipment. Of course, for the TCO, we have found several literature. We had a thorough literature review, and we came up with some parameters to compare them under the same basis. You can go to the next slide. Of course, for our analysis, we had to focus on two different cases. One scenario is the coverage-driven scenario, where we have a really, let's say, rural area. Well, that's what we tried to simulate. And also a capacity-driven scenario, where the capacity demands are extreme, and mostly somebody will have this type of scenario in the city center. Here, this is located in Thessaloniki, which is the second largest city in Greece, and it's where our university is located. So if you go to the next slide. Okay, so this is the first type of results we got. What we can see here is that we tried to have these really huge capacity demands that you can see that on the x-axis, the total data rate in terabps. We had to satisfy that, and we had to deliver this amount of capacity with a specific number of base stations to achieve this goal. As you can see, if we had only one type of base stations every time, the most promising results come from the GNODBs that are terrestrial and operate at the millimeter wave band, so 28 gigahertz, as they require the minimum number of base stations to achieve these goals. The reason for that is generally that the higher the frequency, the higher the bandwidth, so the higher the spectrum efficiency, and thus, although we do have higher path loss in these high frequencies, the high gains we have from putting a higher number of antennas in a small area can compensate for this path loss. So if you go to the next slide, let's go into the TCO here and have a really a look into that. You can see that generally when we have capacity driven scenarios, so a demand of high capacity in a small area, the best choice is to go with terrestrial means. This is not a surprise because we did expect to have this type of results, but this is something that our simulations have proved. So the densification of densely populated areas is about to happen with small cells as they come with lower TCO and with very high capacity. So they provide a really good trade-off. Go to the next slide. Now for the coverage-driven scenario, the trends change quite a lot. As, for example, to cover this huge area I showed before, only one LEO is sufficient. While you can also see that the hubs, which is this green line that you see in the plot, when operating at lower frequency, it can also have similar results. One hubs is enough for areas up to 70 square kilometers. This is because, of course, for base stations being operating at an altitude, as are the aerial and the space ones, they can provide higher coverage compared to the terrestrial ones. And of course, the higher the frequencies, the lower the coverage, and that's why you see this type of results here. So if we go into the TCO, go to the next slide, Konstantina. Here, the outcome is that if we go for coverage-driven scenarios, we have to go with LEOs operating at the 20 and 28 gigahertz, while the second best choice are the hubs operating first at the lower frequencies, 22.1 and then 28 gigahertz. But of course, given that the areas we're about to serve are a mixture in the majority of times of both coverage-driven and capacity-driven scenarios, what we expect are hybrid scenarios, and this is what Ether is all about. So if you go to the next slide. So we had such a scenario where we had a hybrid scenario of different types of base stations, all the base stations I spoke before, and we compared our approach that was developed in Work Package 4, that was a heuristic algorithm that takes into account how to perform the user association, the traffic routing, and the placement of the computational resources. And it does that having as a goal to optimize, actually maximize the energy efficiency. So for our proposed algorithm, we compared that with two state-of-the-art algorithms that you can see on the slide. One is called VCSP and the other is called VNF-PAR. Both of them are actually default criteria for the placement of the computational resources. The first one takes into account the centrality of a node, and it does the routing based on the lowest delay, while the other, for the placement of the computational resources, it actually cares only about the additional capacity, computational capacity needed, what we call gigaflops. While for the routing, again, it takes into account the additional bandwidth demands of the users. It's important here that the scenario we focused is totally tailored to Ether. So you can see these three use cases that Konstantinos spoke about. We tried to take to cover all different services that somebody is probable to see in such a network, in a hybrid network, with specific demands and latency requirements. And our goal was to satisfy these demands, but do it with the highest energy efficiency possible. So if you go to the next slide. So here you can see the TCO results we got. All algorithms, both the state-of-the-art and the proposed one of Ether, all accept all user requests at all times, so they're compared under the same basis. What is important is that our proposed solution has up to 40% almost lower total cost of ownership. And this is because it takes into account jointly all different problems we spoke, so user association, traffic routing, and the placement of computational resources, all done at the same time. And that's why it comes with higher flexibility in the network and can come up with better solutions than the state-of-the-art. So in the end, it deploys lower amount of physical machines and base stations, leading to lower OPEX and CAPEX, and consequently lower TCO. So the important outcome here is that if somebody combines really energy efficient solutions as the ones described with the architecture of high heterogeneity that Ether comes and proposes, actually, you can have really energy and cost efficiency gains. Go to the next one. So my main takeaways from this sustainability, I try to give it very quickly, but of course, I'm happy to answer any questions, is that if we go for really capacity-driven scenarios, we expect to rely on terrestrial means, while for the coverage ones, to rely on non-terrestrial means. But given that we expect to have a mixture of these scenarios, hybrid solutions are here to come for the years to come, are here to be actually the main solution of 6G networks. And of course, if somebody combines these solutions with really sophisticated, sustainable resource allocation algorithms, you can come up with the highest energy efficiency and cost efficiency gains. Thank you very much. I'm happy to answer any questions.
Thank you very much, I'm happy. Yes, we are a bit ahead of schedules, and we can.
We have 3 questions.
Mm-hmm.
They ask probably to Constantino if you can explain a bit more the AI-driven orchestration.
Mm-hmm.
Then why this TCO of LO is lower than the GEO despite the number of satellites needed for the LEO to convert the same cell size of GEO. This is for Agape.
Okay, then I can reply to this one. So
Perfect.
it's why the TCO of LEO, I suppose, it's 1%, okay, is lower than the GEO.
To some slide, Agape, to some figure.
Let me read it and then I can say to you. So why the TCO of LEO is lower than the GEO despite the number of satellites needed for LEO to cover. Okay. So what we take into account into this study is that of course, in order to use these non-terrestrial means, these satellites, we need to have global coverage. So somebody should take into account the whole, for example, constellation cost for the LEO. So take into account the whole constellation, because this is what you need in order to have your LEO network being deployed and operate normally. You take into account how many they are in the constellation, and you can come up with their lifetime, and you can come up with an average TCO per LEO base station. This is what we did. Indeed, in the GEO case, there are only 3, for example, to cover the whole Earth surface, but they come up with a really high number of TCO. So they're much more expensive if you take it as, you just need 3, but you have this type of money needed for the whole of them. And also in the case of the constellation, it's a huge number, but you have to divide it with the number of LEOs per constellation. So I don't know if there's any follow-up question for this.
Yes, there are other 2 questions. Why the use of high frequency with low propagation capability for the satellite and not use the low frequencies?
Why the use of high frequency with low propagation capability? Well, look, the reason why somebody should go with high frequencies, and this is something we do have already in place for satellites, is because, of course, they come with very high bandwidth availability. This is the first reason why. And the second reason is that the antennas get smaller, so somebody can put a high number of them into a small transceiver. And of course, that means higher beamforming gains and finally antenna gains. And these high antenna gains can compensate for this high path loss that we expect to see in these high frequencies.
Okay, then we have one last question from University of Volo, or maybe I will leave directly to you because it's a bit long.
So my question,
you can go straight on the answer.
This is in the project's title, indeed. Has the project been executed, or is it their plan to carry out environmental sustainability? Good question. Life cycle assessment analysis of the proposed 3D architecture or its elements, in addition to the techno-economic analysis already done. Okay, so that's really nice question, and thank you for that. Indeed, Ether was mostly looking at the sustainability aspect through energy efficiency, which is something we engineers are really familiar with. But it's true that being also involved in the sustainability working group, myself and also other people from Ether, we try to have this extra translation into what this energy efficiency means in terms of life cycle assessment, as you say, and also carbon emissions, and other things. We don't have that into the DO, so in the description of the work of the project, but I'm sure this is a really nice area to have a follow-up project, why not, like in Ether 2, that will take the whole cycle management into account, because this is really important. So, but you can find some things that we have done, of course, in our deliverables. We have a deliverable about techno-economic analysis, which is in Work Package 2, so it's 2.3, deliverable 2.3. And also you can find a lot of things about sustainability in deliverable 4.2 that have to do with our algorithms and how they target sustainability.
Thank you very much, Agapi. And there is also the first question. We started with the aspects of the techno-economic analysis, those questions, about the AI-driven orchestration. So I would like to give the floor to Godfrey from Nearby Computing, because they have worked on that. So Godfrey, would you like to say something to elaborate on that, about the AI-driven orchestration?
Konstantinos, though the best approach would have been to wait for this, because we discussed in detail in the next presentations, but just to give a highlight.
Yes.
We try to do sort of closed-loop orchestration where we invoke AI-driven approaches for workload forecasting, which means to do forecasting of the demand, but also to make decisions regarding the orchestration actions. For instance, scaling. So we use AI to decide when to scale, by how much to scale, but also the scenarios to do with migration, where to migrate and when to migrate, in a proactive manner, not reactive as the existing approaches. But I think the entire scenario will come clear when we're discussing use case 3 in this case.
Indeed. Thank you very much, Godfrey. And I think there are no other questions, right?
We have a raised hand, I think.
Yes, I
don't know if
think
it's
it's a
from before.
follow-up to your answer, Agapi. I will allow
Sure.
consent. Okay, Constantine, you should be able to speak now.
Konstantin?
Yeah, cannot.
Yes.
Yeah, now, yes.
Yeah, so just sorry, I haven't noticed maybe, so just that I have raised the hand. Yes, just maybe then just let me use this opportunity to give a comment. Yes, just I fully agree just with you. So that it is a very interesting question just about the sustainability and the life cycle analysis. So that's why I raised it. Actually, we did some estimations of that, so just on the national projects. So if you would be interested to know more, just let me know. I can share with you some results.
Definitely. Please do so. Yeah.
Yes.
Thank you.
And if there is nothing, there isn't something more, I guess we can go directly to use case 1 and my colleague Timo Kellerman from AutoCAD. Let me stop sharing.
Yes, thank you. Yeah, I will start the sharing. Let's see. Is that visible now? I hope so. Okay. All right, yeah. So, hello. My name is Timo Kellerman from AutoCAD. I'm a senior researcher here, and I will present demo 1 of the ESA project. And in this demo, we showcase how flexible satellite payloads and context-aware mechanisms enable reliable and energy-efficient IoT communication over non-terrestrial networks under intermittent connectivity conditions. So let's go to the partners who all contributed on this. So we at AutoCAD, we led this demo and developed several of the key enablers. Then there was Uwe there and Linköping University who helped with semantics-aware mechanisms and the integration of that into the system. And Satellite, they provide general NTN knowledge in the field. And yeah, together we provided quite some output, I think, but you will see yourself in a minute. So I will try to position this a little bit and provide motivation for what we've been doing here in the state of the art section. So first of all, now with a sparse constellation, so you can provide global coverage with a single LEO satellite already, but a few more are surely helpful. In any case, if you don't have a super dense constellation, you end up with intermittent satellite coverage. And there you have to ensure that your satellite also is able to operate independently without feeder link connectivity. Because if it needs to cover the whole globe, you might not always have concurrent service and feeder link availability. Then we saw an issue with existing satellites that are being launched. They're usually single purpose and rigid, so you can't change the purpose. So we thought a flexible payload would help, so you can reconfigure the hardware and the software in orbit and repurpose this according to the need. And then finally, we saw that IoT communication is at times a bit inefficient. So, for example, unnecessary or outdated information is repeatedly sent. So for that, there's a semantics-aware information handling, which helps to reduce unnecessary transmission, which leads to a drastic energy efficiency gain. Now, a bit more on the scenario and context. Here we have a little illustration of this. I don't know if you can see my mouse. Anyway, there's a figure here. There's the satellites orbiting over the Earth, and at the bottom you see ground stations and terminals, and not everything is connected at the same time. So that's this episodic service coverage and non-concurrent service and feeder link that I mentioned earlier. And so despite these connectivity gaps, we want to enable efficient communication, and also offer alternative services. So not just IT communication, but also some RF sensing or other opportunities that are available with the flexible payload. So let me continue to the demo concepts and objectives. So yeah, the first one is the flexible payload. I keep mentioning it, but it's a very important part. Store and forward communication. So with cellular IoT, now it just got into the standard, but when we started this project, that was quite a new idea. So we are able to connect the terminal and under this non-concurrent connectivity, and authenticate it, and then transmit the data. And then also, in order to have this seamless connectivity with the whole constellation, we developed a UE context dissemination mechanism where we put context from one satellite into another and disseminate it across the constellation. And finally, the semantics-aware information handling, which uses this version H of information to assess the information that's generated at the IoT device. Then let's look at the demo setup. So here's a schematic overview. So here on the left bottom side, you see the sensor. So in our test bed, it's hardware in the loop, but it's in the laboratory. So and the sensor is the Raspberry Pi. We have pre-recorded temperature readings that we replay there. And then there's the semantics filter. So the semantics-aware information handling is running there, containerized. And then the narrowband IoT modem for the cellular IoT use case transmitted the data to our satellite. Then the satellite is, we have two of those in the testbed. You will see a photo in a moment. The flexible payload is an ARM processor board and an FPGA, the Xilinx hardware that Konstantinos mentioned earlier. And then we have an SDR on the flexible payload. However, for the cellular use case, we connect to another IF front end, since we did not develop the ENOIC-B hardware software that can run on the embedded SDR, so we use an Mari soft front end there. And then the ground is virtualized. So here we have this Ether-Mano orchestrator. So we developed an extension that can orchestrate the services on the satellite and on the ground. And it's on the satellite, based on the orbit, you can select which service should run over which area. It's a graphical user interface, so that's part of that as well. So this is just virtualized on normal compute hardware. Now here, a quick photo. So after this, you'll see a video where I pointed things in this laboratory testbed, but in general, that's it. It's computers, analysis, and flexible payload hardware, and then some cabling to the Raspberry Pis and modems. Yes, so let's continue to the video. That's about 6 minutes now, so please keep paying attention, and after that I have some more things to say. Let me see. Down there. Welcome to Ether Demo 1. I will give you an overview of our testbed setup before we start showing the individual parts with screen recordings. So up here we have the ground segment virtualized in AMD 64 hardware. Then we have 2 satellites represented by our flexible payload hardware, which consists of an ARM processor, FPGA, and SDR. So we have 2 of those. Now when we use the 3GPP cellular mode, we connect to Amarisoft eNodeB frontends, and then we have the IF part wired up here with splitters and combiners to the user terminals, which run the semantics-aware information handler. Now, the orchestration of ground and satellites, or what part on the satellite is running, the different applications with the flexible payload, is orchestrated here, and that's the overview of the orchestrator. Now, on to the actual demo part with the screen recording. Let's have a closer look at the orchestration and flexible payload operation. The orchestrator is based on open source Mano. We developed an extension that allows an operator to select a geographic region where one or more services should be active. When deployed, the orchestrator dynamically instantiates the service as a container on the selected satellite when it orbits over the selected area. In this example, a satellite orbits over the Iberian Peninsula. On the left side of the screen, we can see the spectrum visualization provided by a service. On the bottom right side, a list of containers that are running on the satellite is shown. One of the services is cellular IoT, and the first crucial operation is a UE attach. On the upper left side of the screen, the UE terminal is shown. On the lower left side, we can see the log of our satellite store and forward function. On the right side, the satellite's eNodeB log is shown with S1 and NAS signaling messages. We start by triggering the attach procedure by rebooting the UE. The initial attach fails because authentication vectors are not yet available on board. Once the feeder link becomes available, pending vectors and subscription information is obtained from ground-based local or roaming HSS and transmitted to the satellites. The subsequent attach procedure succeeds using the retrieved subscriber information. The UE context is now created locally on the satellite, including identifiers, tracking area information, and NAS security context. Moving on to the user data transmission under store and forward operation. You see the UE terminal at the top left again, the PDN log at the bottom left, the satellite store and forward log in the middle, and behind that, the eNodeB log. While the service link is available, we transmit a UDP packet from the UE to the satellite. The packet is encapsulated in NAS signaling and arrives at the satellite, where it is buffered by the store and forward function. Once the feeder link becomes available, the packet is transmitted to the ground segment, where it is forwarded to the PDN. Now, in order to enable seamless multi-satellite operation, the UE context is disseminated asynchronously. The satellite's context dissemination function log is shown at the top left side of the screen. Below them is the UE terminal, and on the right side is the satellite's eNodeB log. At this stage, the service link between the first satellite and the UE is available. The UE has completed the attach procedure with this satellite and can transmit user data packets. Once the feeder link between the satellite and the ground segment becomes available, the UE context created at the first satellite is transmitted to the ground. And then it is transmitted to the second satellite during feeder link availability to this satellite. When the second satellite is passing over the UE, The availability of the UE context on that satellite allows it to seamlessly resume NAS signaling with user data transmission without the need of reattaching the UE. Drastically reduces the signaling overhead. Furthermore, the UE can continue to resume NAS signaling with the first satellite as well as it is shown here. The last part of the demo is the semantics-aware information handling. On the left side of the screen, the UE terminal is shown, which runs the containerized application. On the right side of the screen is the ENOID log of the satellite, where we will be able to see the reception of relevant messages. The system integrates semantics-aware transmission scheduling based on the version age of information. Only relevant updates are transmitted, reducing unnecessary signaling and improving energy efficiency. The mechanism is particularly suited for delayed-to-learn IoT applications over non-terrestrial networks. We have pre-recorded temperature sensor readings from a real sensor in the field, which are being replayed in the system. As you can see in the log on the left, the first few messages are not being transmitted. Now the 8th message is considered relevant by the system and is being transmitted. At the ENOID log, we see the service request message that contains the sensor reading encapsulated in the user data container of the NAS message. The sensor value is hex encoded. Now, after some time, the 16th sensor reading is also being transmitted. At the end, 19 messages were generated and 2 of them were transmitted, which is a reduction of 89% in transmissions. So, yes, that was the video. Now let's have some conclusions. Not again. There we go. Key results and impact. So yeah, you saw all these enablers together in this demo. It's a bit dry, it's just terminals, but that's the proof in the end. So it kind of works what we produce. So the first, the multi-service payload, we can instantiate different services or run them in parallel or alternatively and switch them off when they're not needed. So helps a bit with the energy efficiency, I guess. Then there's a store and forward operation, the two-step attach, and the restoration of the link with intermittent connectivity and the data forwarding under this condition, and context dissemination. So we show it here with 2 satellites, but it scales to any number of satellites in your constellation. I guess the key part is to prove it with 2. The semantics-aware transmission handling, you saw in the example, there were 19, not 18 measurements generated. So you have this significant reduction. So this is the main point how we justify our KPI of energy efficiency. So we wanted to reduce 75%, and we reduce the transmissions much more. So we translated that into the energy efficiency gain. Then the end-to-end coverage support. So with a LEO satellite in a polar orbit, 1 satellite is enough to provide global coverage. And given that it's not quite feasible to have ground stations all over the globe, this store and forward approach enables this global coverage even with a single satellite, and then reducing the breaks or the delays between coverage periods with 1 satellite. The context dissemination helps to provide seamless coverage with multiple satellites. So if you have a bigger constellation in the end, the multi-service support, you saw some IF sensing, there was orchestration. It was also launching the cellular IoT application, which was then shown afterwards. But yeah, we can do both in parallel, or one after the other. So that's a multi-service support. And the heterogeneous services is in one particular application was in the IF sensing, where we do the FFT. We can run it on the ARM processor, but also offload it to the FPGA. So this is an FPGA acceleration, which helps quite a bit to offload this processing burden. Now, there are a few more good outcomes, I would say. So The exploitation is so within this consortium, there was a technology transfer so between I2CAD and Satelliot. This context proxy, which I showed in this demo just now, we transferred that to Satelliot. Then the flexible payload framework at I2CAD, we continue to use it. It actually went into a satellite that is orbiting Earth right now. End of November last year, we launched a satellite which has precisely this flexible payload with this SDR. And now another project is starting, which continues work with that. Then the store and forward narrowband IoT service, Satelliot is commercializing that. And they also proved that this can work with roaming partners. They made a demonstrator with Telefonica and probably some more. The standardization impact is, that was pushed into the standards, the store and forward finally. So release 19, you can read it with VGPP docs. Store and forward is in there with some neat features like a novel reject cost for this attached and an extra timer and a few other things. So yeah, it went into the standard and apparently in ITUT as well. Then post-project life, I already mentioned we have our satellites, so we want to further validate the things we have here in orbit. So the commissioning is not quite close to our satellite. Once that's done, we'll do that. Other than that, we have ongoing intellectual property activities. So both I2CAD and Satelliot filed some patent applications over the course of the project. They are still under secrecy, but well, they were filed, so hopefully they will be granted. So this is a very nice outcome, I believe, for such a project. Yeah, that's pretty much it. Thank you very much for everyone who was paying attention. If there are any questions, there's time now, I believe.
Yes, we have two questions. So the first one is how the handover between the satellite is working.
So this is asynchronously. We have a split core where we have some core components on the satellite and some on the ground. Now, when you attach the UE, there's context being created at the UE side and at the core side. So in our case, this UE context is created at the satellite. Now our special proxy function is able to take this context out of the core there. I mean, it's still maintained there, but we copy it to the ground, and then there we have a dissemination function which sends it to other satellites. So it's in theory fairly straightforward. Obviously, there are some obstacles with specific values, but the most important parts are the unique identifiers of the UE and the security keys. So yeah, if you like to read some of our papers, there's a bit more detail in that. And then I see another question. IoT should have low-cost networks. Yes, this in fact is surprisingly cheap. So that's a big advantage of 3GPP. So we have this vendor interoperability. The UEs, you can already buy Narrowband IoT NTN UEs. We bought them for less than 100 euros. I'm sure they will go down probably to 10 euros or something. And then you can operate them anywhere. And so I believe it's much cheaper than proprietary hardware from existing vendors. And also you're not stuck with a given vendor. And the other thing is launching satellites also became extremely cheap. So our satellite is a CubeSat platform, 6 units. So universities or research institutes can put them together at home basically. And with SpaceX launching a satellite also became extremely cheap, like just a few $1,000s a kilo or something like that. And it's getting even cheaper. So yeah, they are quite cheap in the end, and they are the only real feasible solution to provide this global coverage in the end. And you can do it with even one. Okay, I see more. Any orbital planes? Yes. So as I mentioned before, if you want global coverage for a LEO satellite, you need a polar orbit. So it rotates like this and eventually covers the whole globe. We made some simulations to also analyze the coverage gaps and whatnot. So mostly we did Walker Star constellation with polar orbits to maintain this global coverage. But then from a satellite network operator, you probably want to add some more satellites that are closer, where you have a more inclination angle, because in the end, more population is closer to the equator rather than to the poles. But then, if you do shipping or environmental sensor reading, that is the use case. You still want to cover these remote spots. So we did a basic analysis to ensure that our use case works, and also to establish these timings. But it's not to launch your own constellation. We don't have a proposal for that directly, and it's also in some papers. So you can search me on the Google Scholar or IEEE Explore, and they're openly accessible, so you can read that if you like. I can try and find the links and share them here, or otherwise, again, just search my name. There's not so many with my name. Okay, I think that's it. Thank you, Konstantinos. I think.
Yes, thank you very much, Timo. So let me share. Going to use case 2. Yes.
Stop share. Yeah.
Okay. Right. Share sound is activated. Perfect. Right. This is use case 2. This mode, and we can start. So, describing use case 2, that is titled Unified Radio Access Network for Direct-to-Device Handheld Access. The main contributing partners here are us, the University of Luxembourg, that we host the emulation platform that is based on the Open Air interface. So this is hosted in our 6G Space Lab premises at the university. We have the Aristotle University of Thessaloniki that has provided the energy efficient algorithms for the vertical handover between terrestrial and non-terrestrial genome piece. And we have also the National Center for Scientific Research, Demokritos, that has provided the antenna design at the terminal side in order to enable electronic beam steering, so to track the trajectory of the LEO satellites and sufficient gain so that we close the link. Now, some few words about the state of the art, the background that necessitates such vertical handovers. What we know is that we need to bridge a digital device. There is a big problem that is as follows, that although in urban areas we have a very good coverage with broadband 5G, there are still large swaths of remote rural areas that have either poor terrestrial coverage or no coverage at all. And to substantiate that even further, to talk with numbers, the terrestrial network coverage extends only less than 45% of Earth's landmass. So, using terrestrial base stations to sufficiently cover the remaining land part is cost and energy inefficient for the MNOs. We mentioned about this study of this UK consultancy company that in order to provide full 5G coverage across the UK, you will need to install thousands of additional terrestrial sites, whereas you can provide the same coverage with only a fleet of 60 hubs. So no mobile network operator would go for the solution of terrestrial densification. So cost-wise and energy-wise is highly inefficient. And of course, it's also impossible in some scenarios, such as in maritime scenarios, to have such coverage. And thirdly, there are United States ventures such as Starlink and AST Space Mobile that provide such a coverage already through low Earth orbit satellites. In particular, Starlink runs mega constellations. AST Space Mobile doesn't rely on mega constellations, but it relies on very large satellites. You see here on the right side part, actually such a satellite that has in area the antenna array of 64 square meters. So it's like a court there that can provide even broadband coverage, direct device access from LEO satellites. And the problem with Europe is that we still don't have sovereignty on it. So this is something that needs to change. Now, going to the use case scenario and context. Let us go through the assumption we mentioned before, the aspects. So we assume that the communication with the terrestrial base station is problematic due to either poor coverage or bad link quality. This is a very likely scenario, of course, for remote rural areas. So we would like to leverage low Earth orbit satellites to provide or improve the quality of service needs for the handheld device users. And the key three innovations here are, first of all, the 3GPP compliant energy efficient vertical handover. So I want to highlight the 3GPP compliant. So we rely on open air interface. So this is a 3GPP compliant. So it's not proprietary kind of technology, is fully 3GPP compliant. For this vertical handover from a terrestrial G0B to a LEO satellite 1. So these are innovations that have been brought by us through our emulation platform that is based on open air interface, and the energy efficient vertical handover from Aristotle University of Thessaloniki. And thirdly, we have the terminal antenna design that enables electronic beam steering, as we said before, in order to track the trajectory of the LEO satellites and provide sufficient gain to close the link. The stakeholders that can benefit are, of course, handheld device users that can get sufficient quality of service even when they are in remote rural areas, and then MNOs and satellite operators that can increase their customer base. So they can eventually increase their revenues. Now, going to the demo concepts and objectives. So regarding the objectives is, first of all, to demonstrate the 3GPP compliant vertical handover between a terrestrial G0B and a LEO satellite 1 using, firstly, the open air interface for the run of software stack, and secondly, we use a hardware in the loop setup that is enhanced by an FPGA channel emulator that emulates the realistic low Earth orbit satellite conditions such as high Doppler shift and varying link quality. And the KPIs that we have showcased in this demo is 100% coverage, so we don't lose the connectivity. We migrate the communication from a terrestrial G0B to a LEO satellite 1 when it becomes visible to the terrestrial user, and higher than 70% more energy efficient network with respect to leveraging only a terrestrial macro station instead of LEO satellites. We understand why is that. We understand the huge gains because in night times, in low traffic conditions, we can totally shut down the macro station. The macro stations are very energy consuming. And this is the technology that exists for remote rural areas to provide coverage to such users, such residents in those areas. Whereas if we can shut down, we can rely on if we can shut them down, we can rely on low Earth orbit satellites that are powered by solar energy. So this is how these very high energy efficiency gains come from. Now, a few words about the demo setup. This is our emulation platform, the environment. So, first of all, we have a USRP for the user equipment. We also have two USRPs for the terrestrial G0B and the satellite-based G0B. So the satellite-based G0B, the corresponding USRP is the one on the top. That we denote as G0B1, and the one of the terrestrial is down, the one that we denote as G0B2. And we also see the channel emulator that we have used. This is an in-house channel emulator, so we are developing that at the premises of the University of Luxembourg. So we see here also the links. We use a common clock among the nodes. We also depict here the downlink and uplink links. We use also a 10 dB attenuation in order not to overflow the particular reception links at the channel emulator, so not to have a very high peak power that can fry, let's say, the electronics, and aspects that have been included as parameters. First of all, we use FDTD, so we comply with the standard. The round trip time for the low Earth orbit satellite has been around 4 milliseconds. And we also use a 2x16 IQ bandwidth. And as I said, we use the OpenAir interface, so we are fully 3GPP compliant. Now, going to our video regarding the demo.
Hello everyone, welcome to our demonstration activity related to Ether use case 2 that concerns the provision of connectivity to handheld devices from low Earth orbit satellites. The rationale behind this use case is the fact that there are large areas on Earth that either have poor 5G coverage from terrestrial stations or they have no coverage at all. This is a service that is already being provided by United States ventures such as the ones of Starlink and AST Space Mobile, but unfortunately still Europe doesn't have sovereignty on it. This is something that we change with Ether and this demonstration activity. In particular, we emulate a vertical handover process from a terrestrial base station to a low Earth orbit satellite 1 that uses a 3GPP interface. In particular, we use the OpenAir interface for the radio access network software stack, and we also use an FPGA-based channel emulator that emulates realistic channel conditions from the low Earth orbit satellite to the terrestrial user that consents high Doppler shifts to the order of 18 to 20 kHz and also varying link conditions. This is our testbed setup. In particular, this is the USRP that represents the terrestrial user. This is a USRP that represents the terrestrial base station, and this is the USRP that represents the satellite-based base station. Finally, this is the FPGA-based channel emulator. To proceed further, on the screen we see the illustration of the scenario. In particular, the terrestrial user is initially connected to the terrestrial base station, but the connectivity is poor either because the terrestrial user is very far away from the terrestrial base station, that is a macro one, or because there are high shadowing conditions due to foliage, for instance. Now, as the low Earth orbit satellite gets closer to the terrestrial user, there will be a point in time where its signal-to-noise ratio towards the terrestrial user will become higher than the corresponding signal-to-noise ratio coming from the terrestrial base station. At that point in time, there will be the initiation of the handover process, of the vertical handover process, and the terrestrial user will remain connected to the satellite until its signal-to-noise ratio again becomes lower than the one of the terrestrial base station. Here we emulate only a single satellite, but in a realistic condition we will have a multitude of low Earth orbit satellites in a low Earth orbit satellite multi-constellation, in particular mega constellation, where there will be a continuous handover process among the low Earth orbit satellites. In this regard, when we have low traffic conditions, such as night times, we can totally switch off the macro base stations, and then we get tremendous energy efficient gains because the macro base stations consume a high amount of power, whereas the low Earth orbit satellites are powered based on solar energy. In this regard, with this demonstration activity, not only we demonstrate a continuous connectivity even in underserved areas that the users can be, but also we do that in a very energy efficient way. So, all in all, with this demonstration activity, for the first time, we use a 3GPP compliant handover process, and as well, we bridge the digital divide between urban areas and remote rural areas that have poor terrestrial coverage. So this is of great societal impact. Thank you very much.
So, to go again to the presentation and finish with the impact part, the importance, the economic and societal importance of this use case. First of all, regarding the economic impact, we see here the market size. We see how the revenues increase per year. So what is expected until 2035. So we see the revenues, the increase on the consumer side, on the enterprise side, and the government side. As we see, the biggest portion in the pie is taken by the consumer side. So direct-to-device satellite offers access to new revenues for telcos, which will be worth over $30,000 million by 2035. So these are stats that come from studies in the States. That's why we see dollars, but okay, we understand actually that this is something that will affect also Europe. So Europe will be in part with that. And now we go to some decomposition regarding the revenue opportunity in billions throughout the different areas on Earth. So we see again a continuous increase, and it increases in portion in all the corresponding areas in Earth. And here we see the supply chain on the right side part. So we starting with the customers that require coverage in remote rural areas. Then we have the phone manufacturers that would design and manufacture 3GPP compatible devices so that they can connect to both terrestrial and non-terrestrial stations, LEO satellites. The mobile network operators that will create contracts for service provisioning with customers, they will have these contracts. The satellite operators that will have roaming agreements with MNOs for coverage extension, so that they can use the spectrum in order to provide coverage to the terrestrial users. And finally, we have the large system integrators that are involved in the conception, design, and manufacturing of the satellites and coordinating with launch providers for the satellite development. So, in a nutshell, direct-to-device satellite expands mobile coverage for 570 million plus people, and like a $30 billion revenue is expected by 2035. The final word about the societal impact. There is a great benefit from the environment. We understand that, as we said, in low traffic conditions, night times, the service can be fully facilitated by LEO satellites, and the terrestrial macro stations can be shut down, which is substantial for energy consumption reduction. We can see dramatic change. And bridging the digital device, of course, so providing equal opportunities for high-speed mobile access to both urban users and users residing in remote rural areas. Thank you very much, and I would be glad to take any questions that may have arisen. So I guess we should have questions, right?
Yes, we have two questions. One is it an handover?
Right. It's not an excellent handover because unfortunately we couldn't have the full G0B stack based on the open-air interface limitations. Still, it's not available yet. So we have used an F1 based handover. So it involves a CU-DU split, so it passes through the core network. But this is only through the limitations of open-air interface that didn't have this functionality yet, and it still doesn't have completely. So, I mean, all in all, at the end, actually, the hero of the show here is the vertical handover process. So we were not concerned that much. Unfortunately, I mean, if that was available, we would go with the XN-based handover. That was the reason that we went with the F1 based.
Okay, then the second question is, it's not clear how we will solve the European sovereignty issue.
So we need competitors to Starlink and AST Space Mobile. This is how we can solve that. How can we have competition? We need to have our constellation, our LEO constellation, let's say, eventually mega constellation. And this is what IRIS² aims at. So because now we rely on the United States venture, so on Starlink and the AST Space Mobile for providing direct-to-device coverage.
Okay, and then the last one is if the macro BS is turned off at the night time and there comes a user and it's not connected to LEO, it will have no connectivity, right? What if we have solar operation? We have solar operated HAP UAV as a flying base station to cope with this?
Mm-hmm. First of all, we wouldn't shut down the macro station without having secured that there is a coverage, let's say, a connectivity, that the quality of service of all the users is satisfied. So I'm not sure if it means that a bit means that we can shut it down and without having a LEO satellite that has visibility with the users, or suddenly a new user appears. I mean, because what we have here is that we have a complete, let's say, check control. So supposedly, in a realistic scenario in the future, we'll have a mega constellation, a LEO satellite. So when a LEO satellite uses visibility with the terrestrial users, then the next satellite in sequence, the next satellite of LEO can take the migration and continue satisfying the service to the corresponding terrestrial users. But regarding the second scale about the hubs UAV, sure, because Ether is a 3D ecosystem. So here we started, let's say, with the LEO satellites because these are a more mature technology. Of course, if hubs are mature enough, let's say now we have just some trials that have been performed. Sure, this can also be involved in a hybrid mode. So the connectivity can be provided either by low Earth orbit satellites or by hubs or UAVs. If that answers your question a bit.
Okay, no more question.
Okay, then just without further ado, we can quickly go to use case 3. And let me stop sharing. Thank you for the questions, first of all. I think Hamada is taking that.
Yeah, can you see the presentation?
Yeah.
Yeah, okay. So hello everybody. This is Hamada Al-Shar. I'm Principal Research Engineer Network and System with Collins Aerospace. Today we would like to talk about, a use case that Collins is interested and conceived, and the contribution of our partners in Ether to this use case. As you can see, the big title is AI-driven 3D networks and edge application orchestration. And then we have the title of the use case with architecture for airspace safety critical operations. As all you know, whoever actually interested in aviation or working in this domain is always, when we hear about actually critical operations or airspace, we would like to be sure that we have sort of safe flight and safe and guaranteed message delivery, whether for air traffic controller or whether for the crews of for aircraft. The contributor to this use case, we have nearby computing. Godfrey, actually specifically on edge computing or edge joint computing and application orchestration. And we have Nityai, Alex's Duke, regarding the inference model based on the data given to them to generate inference model and to predict the data analytics. And we have Agabi from Thessalonica, actually for the energy efficiency. As you can see, so the demonstration of this use case actually is focused on the next generation aviation communication networks, building on key project contributions. First, 3D networks routing orchestration, which is led by Collins Aerospace, 3D networks edge joint application and computing orchestration led by nearby computing, AI-driven 3D network analytics led by NetAI. Auth also, they have contributing when it comes to energy efficiency route or energy efficiency and actually even traffic, routing across the network. As you can see here, actually the key point is a 3D network orchestrator, is edge computing, is AI. So all together come in play in order to what we call a resilient network connectivity, resilient computation, resilient application for the future of aviation. So now when we talk about this, there's sort of a state of the art related. So regarding the challenges, what are the challenges here around? So as we can see in such an environment where, from terrestrial to aerial to hub to satellite to even farther altitude, there is what we call, actually the networks to establish a stable network that could offer guaranteed, continuous, reliable integrity and so forth with the mobility, the heterogeneous segment. Actually terrestrial is not like aerial, is not like hub, is not like satellites, and also the dynamic conditions. All this actually will affect in the context of what we call aircraft communication. We have what we call required communication performance. That, along the aircraft, actually when it goes through the different phases from taxi to climb to cruise, and then approach and then landing, all these phases require different what we call required communication performance in terms of data rate, in terms of the delay or latency, in terms of integrity, availability, and continuity. Take all together, we would like to guarantee them through 3D network orchestration. Another challenge, which is the edge computing and application. Often now we see aircraft where actually we have pilots there, but we have also drones where actually autonomous. So you imagine that these different kind of aircraft, from small, tiny, like a mosquito, up to an aircraft, a large aircraft, that all should be connected or should be enabled to have sort of a reliable 3D network connectivity. But in such dynamic environment, for whatever mission, for whatever space they are in, we come back again, that is some of the application might not be feasible to run on these. It has to be run on edge close. So as all of you know, there's something called, we used to, in terrestrial network, follow me cloud, probably will go follow me aircraft, whatever aircraft is, that the edge computing instantiated follow the path of aircraft in order to go for low latency and most efficient computation and achieving the goal of this aircraft service and others. As mentioned by my colleague, terrestrial only cannot really, offer, actually cannot guarantee the services for all the user, whatever user aircraft, whatever actually, when it goes, actually vertically in their space. The integration of non-terrestrial network with terrestrial and hub, also this bring a plethora of application, plethora of services, business opportunity in order to, actually to offer services in this domain. And that's all aligned actually with the European policies when it comes to promote secure, ubiquitous connectivity. Well, of course, the technical offer, actually is focused on the 3D network integration, the edge computation, the AI-driven orchestration to ensure reliable and low latency services for a high mobility application. As I mentioned, it is, a network that has a brain with the AI, and it has also capabilities from orchestration, edge computing, data analytics to energy efficiency. All together come to enforce one thing is connect, resilient, reliable, continuous, and support, actually the service that should be delivered to the users. Now, the use case scenario here, it has sort of vertical domain from airspace, for example, civilian operation. The target is for connectivity and service delivery from edge computing, distributed node close to user, could be airport, aircraft for low latency, AI-driven data analytics in order for optimization performance. And actually, when you have the data that's by the prediction, then you could design that you predict in the future. For example, most of these, when we go, for example, satellite or hub, whatever, these have sort of visibility window, and particularly talk about satellite. And within, if we predict the visibility window, then we can, for example, probably pre-plan handover, pre-plan the connectivity and so forth. And that's, I mean, actually definitely would benefit, I mean, the stakeholder, the operators who would be able to offer services in the space or, I mean, actually for these users. So the key service requirements are continuous connectivity, high reliability, ensuring seamless 3D network operation and effective edge computing for high mobility aircraft and application at whatever altitude. And as you can see, the triangle, we have edge application computing, we have AI-driven analytics, and 3D network orchestration. And I'm sure that in between there's also, if we could, for example, select nodes along the path that contribute toward the optimization of total energy consumption, that will come what we call it the energy neutrality of aerial or even space-based node, and will make the life of these nodes to run for longer in the space. So this is also important to mention. The demo concept here basically goes around the 3D network orchestrator and the edge computing and application, with ultimately to support multi-link redundancy and meeting safety. So here we're just talk, I mean, actually, when we go to the video, and etc., now we'll see that is, when we talk about the orchestration, that is with the many network, that with the heterogeneous network segment coming from terrestrial, handheld, satellite, and what in between, we have many links there, and we have many services that we need to map them into these links. So how the links can be connected, what sort of metric can be used when it comes to the edge computing, how the application could be orchestrated, how it can be instantiated, and of course, resilience is the key. For this, and actually we have within, under the context of ETHA, we have developed this technical concept, which is actually sort of the architecture, you know, what we call the functional architecture. It has the upper part and the lower part. The upper part is focusing on the network connectivity, focus on the energy efficiency services. And for that, I mean, NetAI, the managed using data delivered by Collins, and actually to generate I mean, what called inference model. That inference model along aircraft trajectory would be at any using any custom period will predict the metrics of whole network, but in particular also you could, I mean, resize it to the where the aircraft is, so that we can see which bases around, and then accordingly which metric you can consider in order to select them actually these links. And then that feed also in the 3D network orchestrator, the same 3D network orchestrator just compose the path or select the link based on a single or multi metrics for the efficiency of the network to meet the service requirement of these user, whatever they are. And then if we go into the lower part which is regarding to the edge computing. Edge computing, as my colleague mentioned, and you will see in his coming video, we have two scenarios. We have what we call it, I mean, scaling scenario, but also which is, I mean, sort of, I mean, a follow across the 3D network. When we call, I mean, actually scaling scenario, that is, we have application that is here, that is, we have developed what we call health aircraft application that, I mean, this app receive the data from the aircraft in the sky and try to process them in order to identify if there is any failure of those sensor and accordingly reacts and sort of alarm or whatever it is. So that's a computation. That's also application orchestrated, that is from across the network. And of course, there is sort of to predict how many resources that require for each volume of data, number of aircraft, accordingly, as we will see in the coming summer. So as you can see, within ETHA, we combine the communication and the computing and the computation along with the application to be orchestrated within the 3D network, and that will definitely make the network more robust, resilient, and reliable in delivering and actually the 3D network services. The demo setup when it comes to Collins Aerospace, so we have sort of what we call emulation. That the emulation environment actually has two aspects. One aspect is the software-defined networking environment, where we have that ManyNet, but of course there are other also emulation environment. Within this, we have the data plane. The data plane is constituted from terrestrial and handheld satellite, and accordingly, we use the physics in order to model these, actually links. And so we create, 3D network, and within that ManyNet, within the SD controller, you have SD enabled, actually data plane. And for then that, you have the path computing element according to the services coming that generated from the traffic, safety and non-safety, And when a path is allocated or link is selected for whatever actually service request coming, it will be subject to something called operational service engine in order to condition and to make sure that, actually the service and requirement that generated is met. And here I would like to show you, let's see, I'll show you, as you can see here, can you see my screen? Can you see my screen?
Yes.
Yes, we can, Mother.
Yes, so as you can see, this is a poor interface, but has many things to say. So let me actually tell you something here. Here, as you can see, this is actually a 7-hour flight. 7-hour flights direct from Dublin to New York. And along this flight, actually we place a number of these satellites and a number of hubs. And in the board, actually the airport, they have 5G close by. And the ultimate goal is to make it resilient, as you can see, based on the telemetry and the computation that we calculate for all these links. So as you can see here, we have sort of the flight path, and then you have the aircraft that moves from Dublin to Jenkins, actually airport, to New York. And along the path, it's selected, actually we have the primary, which is the primary path is actually the best path, but not necessarily the path that's actually used by aircraft. And then you have the backup path, and then the active. And then if you see at the bottom here, you have what we call the primary, that's the best path, and then you have the backup, and then the active path, and that follow on real time. So this is, sort of abstract what we could, actually manage to show you. This is sort of what the orchestrator could do. One of many things that looking into the connectivity, and of course, it also for many objectives. One of them, for example, when you use, for example, Go, you have your mobile and you would like to select essentially how much would cost me at the end of the month for your calls. The same thing, the aircraft actually will, along its long trajectory, longer flight, will ask at the end of the day if they have a fleet actually of aircraft to see how much this connectivity would cost us. So from techno-economic, as we can see, 3D network orchestrator need to make a big job in order actually to make it sort of important for you to have sort of affordable connectivity. Now, let me get you to the second part of the edge computing, and then I'll play for you here.
Let's look at the edge application.
I'll leave you with my colleague who's talking about it. So hopefully you can.
This scenario of the demo show. Let's look at the edge application orchestration scenario. This scenario of the demo showcases 3 major capabilities provided by the Ether solution. One is proactive resource allocation, which means the system should be able to anticipate changes in network and the system states in order to allocate resources, thus minimizing resource over-provision and excessive energy consumption. The other is proactive application placement, which means the application is not stationary placed on a single node, but there should be a capability to migrate these across different nodes, depending on where the situation is more conducive. And the other is a zero-touch closed-loop orchestration, which means the system should be able to monitor, decide, and act autonomously with minimal human intervention. Then we look at the architecture of the demo. We have 2 cloudlets, Cloudlet A and Cloudlet B, which are emulating distributed clusters, and these are running the different applications, including the monitoring components. And then we have a moving aircraft, which is experiencing different SNR values to the different cloudlets and generating traffic of different sizes. And then we have the analytics module, which continuously observes and makes prediction regarding the SNR to the different cloudlets and the traffic size as well. The analytics module passes these to the decision engine, which decides when it is required to scale and whether the scaling has to be performed up or down, and also to trigger when it is necessary to perform migration of the application and determining the node to which the application should be migrated. This passes the decision as an action to the Ether orchestrator, which is implemented using the nearby one edge orchestrator, which then enforces these into the underlying infrastructure. Now let's go into the demo. Here we see the nearby one graphical user interface, which is going to be used to manage the different deployed application. and the distributed infrastructure. Specifically under the Ether organization, we should see the components that have been already onboarded, specifically cluster A and cluster B that have already onboarded, which are also visible here. Then the components to be deployed, we have the decision engine and the Collins application that are going to follow. And here we set the configurations. So initially we deploy the decision engine, and we are going to deploy it on cluster A as the target cluster. And we can see the progression here is progressing, but now in sync condition, which means active and running. Once that is stable and running, then we go and deploy the Collins application, and we're also going to choose cluster A as the target application, target deployment cluster. Its progression here, it's progressing now. It's in sync, meaning it's also active and running. Then here we could check the status of the decision engine. The one replica is active and running. And here we now check the status of the flight application, which also is active and running for the two replicas that were initially deployed. And we check the logs of the decision engine here. And we can see it's still waiting for the channel quality matrix, which is actually the SNR values here in that case. Well, in the Grafana dashboard, the system has started to evolve. Here we can monitor the total response time. Here we monitor the CPU utilization, the file size, the SNR of cluster A and cluster B, the power consumption of cluster A and cluster B, and these are the number of replicas that are currently being executed on the application. Interestingly, here we observe that the traffic demand is increasing, which is consequently causing an increment in the CPU utilization of the node, and also total response time therefore is increasing. And we notice here that response time is approaching the 1 second threshold that was set, in which case the decision engine should be able to make this prediction and increase the number of replicas from 2 to a higher value in order to term this quality of service violation that is pending. Indeed, of course, the predictions are happening here. We can see that the replicas need to be increased, okay, to 8 has been predicted. Therefore, here we should be able to see an increment from 2 to 8 replicas. Indeed, it has been done. And once that does happen, we can see that the response time stabilizes. The CPU consumption also decreases, even with an increment in the demand size. But here we notice another pending violation coming in, but this is resulting from the fact that the SNR on clouded A is dropping, while that of clouded B is improving. In this case, we expect the decision engine to make this prediction and term this pending violation as well by performing migration, which actually has happened here, because we see the power consumption on cluster B is increasing and the cluster A power consumption is dropping to 0, which means the application is running on cluster B as seen from here, which means the migration has been triggered in this case. Indeed, we can check what is happening on cluster B, which is where the application is running here by these logs as shown here in this case. And it's being triggered even before the SNR exceeds that. So if you check even the interfaces, we can see that the application is running cluster B, which is the only available cluster at this time here. So the migration has been triggered in this case. So what is noticeable to note here that with the system evolving through this evolution, we were able to maintain the response time within a given bound without exceedingly allocate excessive resources. And these changes, both resource scaling and migration, were being triggered in a proactive manner. For instance, here we can see that the migration was triggered at this point where the application was moved from clouded A to clouded B, where we see also the available node at this instant is clouded B. And the key takeaways through this demo, we've showcased that the proposed Ether solution is able to, 1, anticipate performance issues before they occur, leveraging analytics, thus mitigating quality of service violation, but it's also able to adapt computing resources dynamically, mitigating resource over-provisioning and excessive energy consumption, and it's able to move application to the best location in real time, given a heterogeneous distributed network infrastructure. But we're also able to maintain strict performance guarantees with minimal energy usage. Moreover, we are able to achieve all the above through a full automated closed-loop orchestration framework, which enables reliable and efficient operation for safety-critical airspace communication, as opposed to human-centric approaches.
That's all, right?
Let's look at the edge application orchestration scenario. This scenario of the demo showcases three major capabilities provided by the Ether solution. One is proactive resource allocation, which means the system should be able to anticipate changes in network and the system states in order to allocate resources, thus minimizing resource overprovision and excessive energy consumption. The other is proactive application
Amanda, it's done?
which means the
Yeah, it's done,
application
right?
is not.
Yeah, it's done.
So now we move to the key results. So as you can see, the key point is that is proactive edge computing, proactive application placement. Because in such a dynamic environment, in such a multi-dimensional network environment, you got to be predictive when it comes to network performance, or when it comes to edge computing, what resources would require, and where the application should be reinstantiated. So all these require sort of a prediction, and the prediction got to be right so that you meet, actually, in case for an aircraft to meet the required communication performance, RCB. In terms of computing, you need really to meet, as we know, if you would like to add a payload, as our colleague used case one, to a satellite, this is a scarce resource. So to get, actually, is a resource that is expensive to be added there and maintained, and therefore it has to be used efficiently. So when it comes to the key result and the exploitation of our work, indeed, in the context of 3D network orchestrator, this has been developed here in Collins, and it has a lot of benefits. It also meant to support, actually, a critical airspace operation. It meant to be operating in whatever environment you could imagine, and therefore it is the exploitation of such capability is sort of is needed, and therefore it is, when we talk about, for example, is from a standardization point of view, as this is sort of is based on 3GPP and etc. So that means there will be alignment there. If you'd like to talk from network optimization, etc., and looking about the cost of the connectivity of long term, this is also one of the utility of such. And when we talk about, for example, the edge computing and application, that's absolutely important, because the autonomous that we have is a driverless on the ground. That will happen also. It's happening actually in area layer, network layer, and will happen also somewhere in the space. And therefore, actually, the edge computing would be required from standardization, from exploitation, and elsewhere. In this work, whether actually 3D network orchestration or edge application placement or computing, the bottom line when we do validation is what we call it a closed loop. Closed loop, that there is something to happen, you see it, you analyze it, you decide, you execute, and then you measure, and then you come back again to the loop. So that's actually is important thing. That is what we hear in Edinburgh, the combination of both capabilities, in particular, actually the orchestration, the 3D orchestration and edge computing together would definitely, no doubt, actually enhance the Ether 3D network connectivity, and will be empowered more with NTI data analytics, and also with the energy efficiency, as we say, as we go up in the space, we need really to save the energy and to make them, what we call energy neutrality. That in order, to come to a point where you have sort of energy optimization. I believe with this, I would like to thank you very much for your attention. And if you have any question, I or Godfrey will be happy to answer you. So I'll leave it to you then.
Thank you, Hamada. Thank you very much. I don't see questions regarding this part, if I'm not mistaken, right, Margarita?
Yeah, no question.
No question for that. So, because we have exceeded time by 15 minutes, just a very quick concluding remark in the last slide about what we have seen. So just a moment to quickly share. Right. So we have presented an overview and key achievements of Ether, and we highlighted its sustainable architecture through a techno-economic analysis. Several low and high level enablers were presented related to radio access network advances and the management and registration of the network. And we have also presented elaboratively the successful demonstration activities that revolve around the three use cases. The first use case that is about the flexible payload enabling service provision to semantics aware and delay tolerant IoT applications. The second use case that is about direct to handheld device access. And the third one about airspace safety critical operations. So, having said that, thank you very much all for attending. Please all feel free to follow us on social media. And also, we would be happy if you go to our website to read our public deliverables. And also, we are here to answer any questions that you may have. So, thank you very much again, and have a very nice evening.
Just one small thing to add, slides, the video from the use cases and the webinar recording will be shared in the next days on the Ether website. So,
right. Thank you very much, Margarita.
You're welcome.
So, take care, everyone. Thank you for attending.